Okay, so hopefully you've mastered series and parallel circuits. Now we're going to move on to part number 3, complex circuits. So just like when we did series and parallel circuits, the first thing that we always have to do is identify our circuit. So let's chase electrons here. The plus is at the top, the minus is at the bottom. And if we follow our circuit, it looks like we got a fork in the road, which tells us it's a parallel. And then it meets back here. And we're back into one path, and that's a series. So this is actually a combination of a parallel circuit, in this case of R2 and R3, and that parallel value will be placed in series with R1. So what we do is we assign this what we call an R equivalent. So whenever we're solving a complex circuit, we have to solve all the parallels first. Now this one only has 3 resistors, but you could have 2 parallels or 3 parallels in series with 2 or 3 resistors. But we're going to take it slow right now and just do it with 3. So we have 2 resistors in parallel, which is R2 and R3. So we're going to use our reciprocal formula, just like we did with our parallel circuit. So we're going to do 560 x negative 1 plus 470 x negative 1. You'll hit equals and then do the reciprocal one more time. And that's going to give us 255.533 ohms. Now, anything that's remaining in series will get added to that 255.533. It's important that you remember that number. We call that R equivalent because you are going to need it for a future problem. So you want to write that down, scribble it on your notepad or next to your circuit if you're drawing it out, because you will need that for a future formula. Okay, so we're going to take the 255.533. We're going to add it to 820 ohms, and it's going to give us a value of 1,075 ohms, or 1.075 K. So let's just do 1,075, 1.075. Hit your little C for correct. It's going to tell us it's right. And now we're going to solve current just like we did in the series and just like we did in the parallel. If I want I total, I'm going to take my E total of 18.620 volts, and I'm going to divide it by 1,075 ohms. And it's going to give me a current total of 17.320 milliamps. Check our work, and we're good there. Okay, so first we have to solve VR1, VR2, and VR3. After we solve those, then we can then solve IR1, IR2, and IR3. Now, one thing I can tell you is we really don't have to solve IR1, because if we go back to our first formula, we know that current total is going to be the same in any series part of the circuit. So we can actually say that IR1 is 17.32 milliamps. So that's one that we know from Kirchhoff's law. VR1, VR2, and VR3. Well, VR2 and 3 are going to be the constant across this. How do we solve that? Well, we know that V equals I times R. Well, what is the I through R2 and 3? It's going to be the constant current of 17.32 milliamps. But what is the R? Is it R2 or is it R3? It's neither. It's the R equivalent that I told you to write down earlier. So it's 255 ohms, and we're going to multiply that by 17.32 shift milliamps, and that's going to give us 4.41 volts, 4.416. And don't forget, it's constant across the parallel, so you're going to put that in both of them. Now, VR1 is easy. VR1 will be IR1 times R1. We already told you that IR1 is 17.32 milliamps. And we're going to multiply that 17.32 times 820 ohms. And that's going to give me 14.202 volts. So if we take the voltage across R1 and the voltage across R equivalent, that means you only count this once. 14 and 4 is 18. 0.4 and 0.2 is 18.6, adding up to our 18.62 volt source. Now, how do I figure out the current through R2? Well, I is E divided by R. So you're going to take the voltage across R2, 4.416, and you're going to divide that by the value of R2, which is 560 ohms, and it's going to give me 7.885 milliamps. So let's correct that. Let's check IR3. So that would be VR3 divided by R3. So 4.416, we're going to divide that by the value of R3, which is 470 ohms. And that's going to give me 9.395 milliamps. Now, if you remember earlier, I said that the sum of the currents in each parallel should add up to I total. Well, it looks like it does. Let's check our work so far, and it looks like everything is right. Power is always easy. Power is amps times volts. Doesn't matter if it's series, doesn't matter if it's parallel, doesn't matter if it's complex. So the I total is 17.32 milliamps, and we're going to multiply that by our 18.62 volts. And that's going to give us 322.498 milliwatts. PR1 is simply VR1 times IR1. And that's going to give me 245.978 milliwatts. PR2 is VR2 times IR2, and that's going to give me 34.665 milliwatts. And finally, PR3 is VR3 times IR3, and that equals 41.488 milliwatts. How do I know I did it right? Because this plus this plus this, PR1, 2, and 3, should add up to power total of 322.498 milliwatts. Take your time and practice some of these problems until you've mastered it using the ETCAI software, and you will be one step closer to being DC Electronic Module 1 certified. Good luck.